quantum computing, Christian Roos. Christian is a true expert of controlling and manipulating ions in crystals, and has been very successful in using this system for simulations of spin systems and studying magnetisms. So Christian, I would like to invite you to take the floor. We are looking forward to your presentation. So the title of the presentation is Quantum Simulations with 1- and 2-dimensional ion crystals.
Yeah, good morning. I would like to start by thanking the organizers for the invitation to this meeting. When I accepted the invitation, I thought Munich is not far away, until I realized that we're talking about Sonthofen, and it takes about 6 hours to come here by public transportation. And when I figured this out, I thought, no, this is not what I want to do. And so I decided to make this my first carbon-neutral conference participation outside of Innsbruck. And so far, this has been a pleasant experience. So I'm going to talk about quantum simulations with trapped ions. So it's not so much about quantum computation, but rather about quantum simulation. And what I want to cover in my talk today are experiments mostly with linear strings of ions. I will briefly talk about 2D crystals at the end, but I will start with an introduction to the basics of trapped ion quantum simulations, and then I will present 2 recent experiments that we have been doing, where we, in the first experiment, investigated non-equilibrium dynamics and spin change with long-range interactions, and then in a second, still ongoing experiments, where we used variational quantum simulation for probing ground states of spin change with short-range interactions. And at the end, I will say a few words about planar crystal experiments. Yeah, quite a number of people have been involved in these experiments. And here I just want to highlight the contribution of Manoj Joshi to the experiments that I'm going to present. And I also would like to mention that we had a very fruitful collaboration with our theory colleagues in Innsbruck, the Peter Zoller and co-workers, but also on another experiment with Michael Knapp and co-workers from the TU Munich. Let's start with quantum physics with trapped ion crystals. We use radio frequency traps to trap these charged particles in effective harmonic potentials that are anisotropic, with trap frequencies that typically range between 100 kilohertz and 4 megahertz. And the trap frequencies then set the typical distance between the neighboring ions in such a crystal, and therefore they set the longest length scale in this problem, the ion-ion distance. And this distance is typically on the order of a few micrometers. And that is important for 2 reasons. First of all, it enables us to spatially resolve the fluorescence of the light emitted by the ions, since this is the distance is quite a bit bigger than the optical wavelength of light, and therefore we can measure ions ion per ion. We do not measure just the ensemble, but we measure the fluorescence of individual ions. This enables us to probe the quantum system particle per particle. Secondly, for the same reason, we are also capable of individually addressing ions by strongly focused laser beams, and so we have also single qubit control over the system of trapped ions. And then you see that the distance between ions is orders of magnitude bigger than the atomic length scale, and this is good and bad at the same time. It is good because we don't have to worry about the quantum state of other ions influencing the state of a particular ion in this chain. But it's bad if you want to turn the ions into an interacting many-body system, because it means that we have to engineer the interactions that we want to create. They are not naturally present in the system. But let's start with encoding quantum information in ions. We work with calcium-40 ions, and the calcium-40 ion, singly charged calcium-40 ions have a ground state in addition, a metastable state with a lifetime of about a second, which is long for the duration of our experiments, and therefore we can encode a qubit or a pseudo-spin 1/2 system in this 2-level system, and we can coherently manipulate it with a narrowband laser at 729 nanometers. We can also measure this qubit with high fidelity by trying to excite the ions on this transition from the S1/2 to the short-lived P1/2 state, which cannot decay to this metastable state here. And therefore, if we, this measurement then is a protective measurement which will give rise to a fluorescing ion if the ion is projected into the S1/2 state, and to an ion that does not emit any fluorescence if we project onto this metastable state. And so if I identify the S1/2 state with a spin down state and the D5/2 state with a spin up state, then we carry out here a spin projection along the Z direction. We can measure other spin projections by coherently rotating this qubit prior to the state measurement. And we can also, of course, then correlate outcomes on different ions and measure arbitrary correlation functions. The ion trap that we work for confining linear strings of ion is sketched here, and it provides us with a very anisotropic potential. And in these anisotropic potentials, we can then trap strings of up to 50 particles. And as you can see here, we can nicely resolve the fluorescence of these ions in the chain. And then, so in this case, this would correspond to all ions prepared in the spin down state. And then, using a strongly focused laser beam, we can manipulate this spin chain, for example, flip the center spin here to up, and then you see that here there's one ion that does not fluoresce, but of course is still present because otherwise the equilibrium positions would be different here. And we can move this beam around and use it for preparing input states and more generally for carrying out arbitrary single qubit operations on this spin chain. Now, the anisotropy of the potential determines the crystal configuration. I told you if we make the potential very anisotropic in such a way that there's one weakly confining axis and two strongly confining axes, then the equilibrium position is a linear chain of ions. Whereas if we make the potential strongly confining along one direction and weakly confining along the other two, then we have the possibility of creating planar crystals of ions. And here the equilibrium positions are determined by the equilibrium of forces between the confining trapping potential and the repelling Coulomb force that acts between the ions. And this Coulomb force not only determines equilibrium positions, but also gives rise to collective modes of motion, because if one ion moves a little bit, then the other ions see that the potential changes, the Coulomb potential, and therefore they have to move as well. And for the linear strings, it means that we get collective modes of motion that decompose into a set of n axial modes if you have n ions that describe the motion of the crystal along the direction of the string, and two n sets of motion that describe the transverse excitations of the ion crystal. And similarly, for the planar crystals, we have coupled motion in the plane, so we have two n modes of motion that describe the in-plane motion, and then a set of n collective modes of motion that describe the out-of-plane motion of the ion crystal. And these motional modes, if the ion motion is cooled to low temperatures, has to be quantized, and so we have a collection of harmonic oscillators, and control over these harmonic oscillators is key to inducing effective spin-spin interactions between the ions, as I will discuss next. So what you can see here is, and maybe let me just go back. So this is an example of the mode spectrum. So here we have the axial modes of motion, and then there's a cluster of modes which bunch in frequency space that describe the transverse excitations. And these transverse modes of motion are important to us because we can couple to these transverse modes of motion with laser beams and create interesting spin-spin interactions by such a coupling. And that's what you can see here. So if we take a spectrum of the qubit transition, then if the laser is resonant with the atomic transition, you see then we can flip the internal state of the ion without affecting the motional state. But there are also sidebands present where each line here, so this is experimental data, there are these red sidebands and the blue sidebands where each line corresponds to coupling to one of these collective modes of motion. And if the laser is detuned from the transition, then whenever you flip the state of your qubit, you also increase the vibrational quantum number of that particular oscillator by one quantum of motion. And similarly here on the red sideband, you have a James-Cummings dynamics where you decrease the vibrational number of quanta by 1 unit. Now, how can we make use of this coupling that couples the internal states to the motional excitations to create entangling interactions between the internal degrees of freedom. For this, we use a bichromatic light field, shown here, that off-resonantly couples to this cluster of vibrational sidebands. And then we have processes like, for example, the one sketched here, where a pair of ions starts in the spin-down state. And then you have an absorption on one of these blue sidebands that flips one spin and increases the vibrational quantum number by 1 unit. And this can be followed by an absorption on a red sideband that flips the second spin and decreases the vibrational quantum number back to the state where it started from. And if the tuning is big enough or the coupling strength is weak enough, then we can describe this in second-order perturbation theory, and then the states that mediate the coupling are only virtually populated. And you can see that we get then here an effective spin-spin coupling where one spin can flip provided another spin flips as well. And there's a second process with the same coupling strengths that gives rise to a hopping of spin excitations. And for this reason, we can describe this interaction then by an effective Hamiltonian of Ising type, where Jij is then the coupling matrix that describes the coupling strengths between pairs of spins in the system. Now, what does this coupling strength look like? In second-order perturbation theory, that's given by this expression, where you have here basically the recall energy multiplied with the intensity of the laser, inducing the coupling. And then there's a sum over all vibrational modes that contribute to this coupling. And in the denominator, you have basically the tuning of the laser from that particular mode frequency. And here, these BIMs and BJMs, they describe the amplitude with which a particular ion I participates in the collective mode M. And this matters quite a lot. So let's take this example where I have 11 ions. The highest frequency mode with the smallest detuning is the center of mass mode of motion. And in the center of mass mode of motion, all the ions oscillate with the same strength. And so these are the BIMs, which I sketched here as blue bars. And therefore, the center of mass mode of motion mediates an all-to-all coupling with the same strength between all ions and gives rise to a spin-spin coupling matrix, which is shown here, which with an antiferromagnetic coupling of the same strength. So color encodes whether you have an antiferromagnetic coupling or a ferromagnetic coupling. Now, what happens if I add the contribution of the second mode, which is the tilt mode of motion, to this coupling? Then it gets more interesting, because now you have ions which are nearby, which move in sync, and they reinforce the coupling of the center of mass mode of motion. Whereas ions at opposite ends of the chain, they move out of sync, and their contribution destructively interferes with the contribution of the center of mass mode of motion. And now the spin-spin coupling matrix gets some structure, and I can add more and more modes to this. And in the end, I end up with a coupling matrix which is more or less homogeneous across the chain and which falls off with distance. And this coupling matrix can be, to a good approximation, described by a power law interaction, where I have then a spin-spin coupling matrix with a coupling strength that is inversely proportional to the distance between the ions raised to some exponent alpha. And this exponent alpha is bounded by 0 and 3. I get to 0 if I tune the laser very close to the center of mass mode of motion, so that I get an all-to-all coupling of the same strength. If I tune it very far away, then I get something which looks more like a dipolar coupling, but these are limits that can only be reached in the limit of vanishing coupling strength. So typically the exponent that we're talking about here, alpha, is in the experiments between something like 0.5 and maybe 2. There's one more thing we can do. We can also detune the frequency of both lasers by the same amount. So far, the sum of these two frequencies here matched was equal to twice the transition frequency. If I detune both lasers, for example, to slightly higher values, I make the process where ions start out in the same electronic state and get flipped off resonant. So I can suppress this process. But I do not suppress the flip-flop term where one ion is excited and the other one is in the lower electronic state. And therefore, then this Ising interaction then becomes something like an XY model where I have spin excitations that can hop across this spin chain, provided that this detuning, which is equivalent to adding a transverse magnetic field, is sufficiently big as compared to the spin-spin coupling matrix elements. Now, the easiest experiment to test this is to take a spin chain in the slip for this XY model, flip one spin, switch on the entangling interaction, and observe how these spin excitation starts to propagate across the spin chain as a function of the interaction time. And that's what is shown here in this false color image. And you see here that they spread out over the entire spin chain, and there's some interference pattern in between, which is quite convenient for us to calibrate this interaction, because we can easily calculate what we expect to find and compare experimentally what we have in our experiment. I also want to mention that, of course, if you have an excitation which can move left or right, then this is a coherent process, and therefore we expect that this propagation of excitation is linked to distribution of entanglement across the spin chain. And we can measure this by measuring reduced density matrices that indeed show that this process creates entanglement across the ion chain. Now, we can also do something more complicated and prepare, for example, a 50-ion spin chain in a nil state initially and switch on these interactions. And then you see that these localized spins get delocalized over the ion chain. And at this point, when you measure reduced 2 or 3 qubit density matrices, you find that all the ions are entangled with their neighbors. And when you go to longer times, then these correlations start to propagate. And then measuring reduced density matrices yields density matrices which are more and more mixed, because the entanglement is no longer contained within the subsystem that you measure. And then then we expect to have a very complex entangled state, and measuring the entropy of such a reduced density matrix then is a measure of how much entanglement we have, provided that there's no decoherence present, which also would raise the entanglement. We have done experiments along these lines, which show that indeed the entire in smaller spin chains, that the entire state of the spin chain remains in a fairly pure state, even though the subsystems look completely mixed after a while. Now, more recently, we became interested in another question, and that is what happens if I look at the propagation of an excitation of an excited spin across a high temperature background that I can prepare by randomly preparing the other spins in up and down and averaging over different initial states. And then we can try to ask, is there any, then you expect that these excitations start to scatter off the other excitations. And the question is there a hydrodynamic description of a diffusive or maybe a super diffusive transport? And in order to investigate this, one can measure correlation functions in space and in time. So you can ask, what is the correlation function between the spin that is initially localized in the center here at time t equals 0 and at a later time at a different site? And we have done this, but the problem, of course, is that when you want to track what happens to one spin excitation across a long spin chain, then the contribution of this single spin to each chain is quite low. And at the same time, you have randomness because you prepare these ions randomly in up and down state, and then you would have to average a lot in order to bring down these uninteresting fluctuations to a level where you can see these correlation functions here. But since we can control the state of the entire spin chain initially quite well with this localized laser beam, you can also try to make use of a trick where we prepare these initial states in conjugate pairs. That is, we flip the central side here, and then for the other spins, we prepare one state and a second state where these spins end up in opposite states. And if you average over them, then it's possible to smooth out these fluctuations that do not contain any interesting information and really measure these correlation functions. And here I just show you one example of an autocorrelation function where you can see that this spin excitation here moves away, and then there is some equilibration process where it spreads across the spin chain. And when you measure then these correlation functions in a spatially and temporally resolved manner, then it's possible to show that indeed a hydrodynamic description captures the dynamics that we have. And we see then, depending on the range of the interaction that we implement, that we see either a diffusive transport or some super diffusion because of the long-range nature of the interactions. And this was recently published, and there's parallel work that was published by the Bloch group in the same issue. Now, I don't want to say much more about this, but rather discuss a second experiment that we have been doing. And here we made use of variational quantum simulation for characterizing entanglement in a quantum antibody system. Now, variational quantum simulation is about programming quantum simulators. So the idea is that we have a state, and we can now carry out a number of operations on the state where we entangle the ions and have single qubit operations. And the rotation angles that enter here are then described by a vector which results in a complex entangled state of the spin chain here. And carrying out measurements, we can then now make use of a computer that takes the measurement as an input and that tries to minimize a certain function of interest by providing feedback so that you optimize the rotation angles that you have in order to minimize a certain function that you want to minimize. Like, for example, in a variational quantum eigensolver, where you have a target Hamiltonian described by some lattice model with composed of a number of terms, and where you try to find a variational function that minimizes this energy. And if the family of variational function is big enough so that it encompasses the ground state, then you can hope to prepare the ground state by such a feedback loop that tries to minimize this energy, and the energy can be calculated by taking the expectation value of the Hamiltonian, which is nothing else than the sum of the expectation values of these correlation functions that we can easily measure. And we have done this recently with a Heisenberg spin chain of 50 spins as our target Hamiltonian, and where we use our naturally existing XY interactions and single qubit rotations as a resource for preparing states that we achieve by having 5 layers of entangling interactions followed by single qubit rotations. So in total, we have 10 variational parameters, and then the outcome is an energy minimization where we look for the global minimum in this 10-dimensional search space, and where we are able to get to values which are, with 50 ions, I cannot claim to reach the ground state, but we can prepare low energy states of this Heisenberg spin chain. Now, what can we do with this now that we have prepared a state? We can now try to carry out measurements to characterize the properties of this state. And so what we have is we might be interested in a subsystem of this big state and want to find out about the structure of the reduced density matrix on this subsystem A. And you can mathematically decompose it by carrying out a Schmidt decomposition. And if you have an entangled state, then here we have a sum over terms where xi is then the rank of this reduced density matrix. Now, you can, instead of talking about the reduced density matrix, you can also talk about the entanglement Hamiltonian, which is nothing else than a Hamiltonian that gives rise to this density matrix if you exponentiate it. And also about the entanglement spectrum, which is linked to this coefficient here in the Schmidt decomposition, which contains information about entanglement measures, and where also it has been shown that this entanglement Hamiltonian can be used to detect topological order or phase transitions. No, the question is, can we measure the entanglement Hamiltonian? We can do this for small subsystems by quantum state tomography. However, this is costly because we need many measurement bases in order to investigate bigger systems. But we can also try to get an idea about this entanglement Hamiltonian by using knowledge about its structure. And this knowledge comes from quantum field theories, where you might also have a vacuum state and then look at the reduced density matrix here of a subsystem of your state, where you also have an entanglement Hamiltonian that has been shown up, that shows up here. And for relativistic quantum field theories, there's a theorem by Bissognano and Wichmann that have shown that this entanglement Hamiltonian here has a simple structure if you look at a half space, where this function beta here, so first of all I should say, the entanglement Hamiltonian then, according to the theorem, is nothing else than your system Hamiltonian multiplied with a prefactor which rises linearly from this partition of your subsystem. And so somehow this looks like a local temperature that you have, which is high close to the border and which drops off. And so this high temperature then is due to breaking in quantum correlations between the two subspaces here in this region, and then the further you go away, the smaller it gets because the system is more pure. And similarly in conformal field theory, there's something similar. If you look at a sub-region here, then you can find something similar where you have the entanglement Hamiltonian, which is basically equal to the local terms that you have multiplied with a function here, which can be parabolic. And these concepts carry over to spin lattice systems. and for this Heisenberg model that we are working with, there is a description in terms of such a conformal field theory. And so the question is, can we make use of this? So we have our Hamiltonian here of the Heisenberg type, which is a sum of local terms where I have a spin coupling between neighbors. And the question is, can I now make an ansatz where I assume that my entanglement Hamiltonian is the sum of these local terms multiplied with some weights, and possibly some further terms that might show up. And then I might be able to carry out measurements where I can make use of this description and see whether the data that I measure fit this description. And also, if I have further data, I can try to verify whether this ansatz is good enough or whether I have to modify it by including further terms. And so here we have now our Heisenberg spin chain, and then these HL, for example, this would be a coupling term like sigma x of spin I with I plus 1. And when you carry out DMRG calculations of the ground state here, then you see that for different system sizes, you indeed find something which looks like a parabola. Then our theory colleagues have also simulated the state that we believe to produce with our variational quantum eigensolver, because we have a certain set of parameters. And when you take this state here and calculate the form of this entanglement Hamiltonian, you see that once again you have something which looks like here, which has this parabolic structure. And when we carry out tomography in the experiment using the recipe I just explained to you, then we have a nice match between what we find experimentally and what has been predicted experimentally, theoretically. And doing this, we can even go a bit further. So we can try to prepare a ground state, and then starting from this state, make modifications to the circuit that prepares the state, such that we heat up our state a little bit. And then what do you expect to see? So if you're in the ground state, then we should see these parabolas. If we have a high temperature state, assuming that we have a system where the subsystem is able to equilibrate with the bigger system, then we should have a description of our reduced density matrix as a thermal state, which means that now there's just one temperature, which means that we should here have something like a rectangular function instead of having a parabola. And an experiment with 11 ions, and here we carried out quantum state tomography of a 5-qubit subsystem. We indeed see that when we start from something which is close to the ground state, where we have these parabolas, then these coefficients go down, which means that the temperature goes up, and also this curve flattens. So in the middle, it goes down further than what you have here at the border. And you see that then we have a transition from entanglement entropy by having entanglement between the subsystem and the rest of the system to a system where we have also thermal entropy in addition. So much for that. As the last point, I have one slide on first of all, I could talk about correlation spectroscopy, which I will not do because of limitations in time. But in another experiment, we have these two-dimensional ion crystals. And we hope to do also quantum simulation with these two-dimensional ion crystals because they provide a way of going to larger number of ions and at the same time have some interesting geometry, because now we are no longer have only a spin chain, but rather we get something like triangular lattices of spins that we can work with. In this case, we want to couple to the out-of-plane modes of motion for mediated entanglement, similar to what we have with the linear strings. And what you can see here, for example, is the set of red sidebands of a 42 ion crystal after Doppler cooling. And we have control over the motion by using ground state cooling, using electromagnetically induced transparency. And you can see that when we apply this, these sidebands vanish because there's no level you can excite an ion to if you're already in the ground state. And what is missing still are the entangling actions. We are working on this and also on the local control that we want to have. But what we have already seen is that we can prepare interesting non-classical n-qubit correlations that are of interest for experiments which rather go into quantum metrology. And with that, I'm at the end of my talk. So I hope that I could convince you that trapped ions are an interesting system for creating long-range spin models. And I showed you two experiments, one about this hydrodynamic description of late time dynamics in long-range interacting spin change, and more recently about measurements of these entanglement Hamiltonians. Thank you for your attention.
Thank you, Christian, for the presentation of these beautiful results. We are slightly over time, but I would like to see whether there is one or two short questions to ask Christian.
Hi, I have a question about the function that you call GL, or at first it was beta, like the local temperature. I wonder if there can be like different shapes, and if they can tell you something about the structure of entanglement in the system, like maybe when you have area law or volume law, like what do you expect that function to look like?
Yes. So if we prepare if we're able to prepare ground state, then we would expect to have an area law, and somehow this parabolic structure, I think, it reflects this area law, because you here in this region you break your quantum correlations, whereas in the bulk of the reduced subsystem you're far away, and you therefore have something which looks more like a low temperature state, and the bigger you make your system, the higher this should get. Whereas when you have a highly excited state, then you should rather have a volume law of entanglement.
Okay, in the interest of time, I would say that we stop here the question and invite you to address Christian then later in the coffee break. So thank you very much, Christian, again.